All right, you guys, and welcome back to another AP Physics C video. Today we're going to be deriving the rotational inertia of a non-uniform rod about its end. So you could do the same thing about its center. You would just change the integration bounds and follow the same process. No matter what the lambda is, you'll still be taking dm dx and using that to find the rotational inertia. So it's kind of the same process, and I challenge you to do different problems. But today we're just going to do this problem, and if you guys have a problem that you'd like for me to do, please put it. I'll consider doing a major derivation on it. But yeah, knowing that, let's just get into it. So this rod has linear mass density lambda, meaning it's not uniform density, so we can't say that lambda is equal to m over L. We're going to have to follow a different process. So we'll start with our rotational inertia equation, as always. R squared, oops. I don't like the way that, okay, is integral, integral R squared dm. Knowing that, we're going to go and say, we're going to actually do the same thing here. We're going to always, as always, we're going to visualize a little dm that corresponds to an infinitely small dx, right? Because I'm going to visualize a little piece dx that is, oops, that is x away from the origin. And that dx has to have a dm. So the rotational inertia is going to be the sum. Well, I shouldn't say that. We'll think about it this way. We're going to go through lambda because I know lambda is dm dx. So I'm going to say that lambda dx is equal to dm, right? So now what we're going to say, we're going to take this lambda that is equal to gamma times x squared, and we're going to sub that in here. We're going to say gamma x squared dx equals dm. Now we're going to transform this integral. So this integral, our integration bounds, we know have to be from 0 to L because we only want to sum up all the little dm's that are r distance away from the origin from 0, right, to the length of this. Otherwise, we'd be imagining some other rotational inertia, which we don't need, right? But r is the distance away from the center, which now we know will turn into x squared. And I know dm is gamma x squared times dx, so I'll just sub that in, gamma x squared dx. Oh, well, now I can take the constant, which is gamma, out of the integral. And this will become, sorry, not x to the fifth, x to the fourth dx. And now I'll finish this integral by computing it. And this will become x to the fifth over 5 from the bound 0 to L. If you can see what's going to happen, that's very good. Because this, we're just going to do that same process, L to the fifth minus 0 to the fifth divided by L, divided by 5, right? This will turn into 0 because 0 to the fifth divided by 5 is 0. And now I'll sub in for gamma, which is 3m L to the third, and now times L to the fifth over 5. And now these L's are the same, so I'm just going to replace one for the other, because I should have written it like that initially. And L to the fifth divided by L to the third is going to give me L squared, so the rotational inertia is 3/5 mL squared. Done. So hopefully that helped, but I encourage you guys to try with different lambdas, and just as a parting gift, this is one lambda you should try. You should try 1 plus 1 over x, right? You should try that to be your lambda, and then tell me what you get in the comments, because this would symbolize kind of a rotational inertia that looks kind of like a rod that looks kind of like that. Not a rod, but something that looks a little bit like this, right? Because the lambda, the mass is getting smaller and smaller and smaller as you increase x. So yeah, let me know what you guys think. If you guys have any more derivations you'd like for me to do, I'll do them. But yeah, hopefully this helped, and I'll see you guys in the next video.